Hi guys, these are some of the work problems from chapter 14 that we weren't able to cover in lecture. Now some of these we actually did cover in lecture. I just thought it might be nice to have them included in this recording, so I may go through them a little bit faster than what we did in class simply because you've seen them before. Now one of the things I would highly recommend is that when you see a problem up here, pause the video, try working yourself to see if you can understand it on your own, and then watch the video and see how I solve it. And that'll help you with the learning process. But the nice thing too about these videos is, remember, you can always pause it and rewind and replay anything that you need to. Now this first problem, this example 14.2, we've already done in class, and they want us to calculate the equilibrium constant for this reaction of converting ammonia into its elements. Now to do this, we have to look up the equilibrium constant for the reaction of nitrogen and hydrogen. So this would be given to you. And for this reaction, notice that we actually want to find the equilibrium constant for the reverse reaction, and yet the coefficients are a little bit different. So we need to reverse the reaction and divide by 2. So we need to use our K value that we found for this reaction and convert it to a new K value which suits the way that it's written for this in this manner. Now to reverse the reaction, remember that the K backward equals the inverse of the K forward. And also when we do the K new and we have new stoichiometric values in front, then we use the K old raised to the n power. So we're starting off with our initial reaction. We're going to reverse that reaction, so we just simply written in the opposite direction. So we take the K2 being the 1 over K1. Now we're going to divide everything by 2. And so when we divide everything by 2, we raise that to the 1/2 power. And so that's the same thing as taking the square root. And so our new K prime value for the reaction as it's written in the problem is 5.2 times 10 to the minus 5th. Now in this next reaction, they want us to find the Kc for the given Kp value. So they give us our balanced chemical equation of NO and oxygen combining to make nitrogen dioxide. Now remember, the Kp is written so that the Kp is where the amounts of materials, the products and reactants, are given in pressure, and the Kc is in units of concentration. So to convert from Kp to Kc, we use this equation here. And this would be given to you, so this is not something you have to memorize, so you'd find this on the cover sheet of your exam. So if we want to find Kc, we can simply rearrange this equation so that Kc equals Kp divided by the RT raised to the delta n. So this is just the rearranged equation. And to find the change in the number of moles, it's always products minus reactants. So we have 2 moles of gas that are produced, so that's where the 2 come from. And we've got 3 moles of gas that go into making that 2 moles, so it's 2 minus 3 equals -1. So the change in number of moles of gas is -1. So using our equation for Kc, we simply substitute those values in. So the Kp value, the gas constant, so 0.0206 liter atmospheres per mole K, times the temperature in Kelvin, raised to the -1. And the algebra says that that should be 5.8 times 10 to the minus, or 5.4 times 10 to the 13th. And remember, K is a unitless number, so we drop those units. And because there are more moles of reactants than products, then the Kc should be larger than Kp, and that's it. So this kind of helps us to make sure that we understand what's going on and double check our math. This is another problem that we've also done before in class, and we're looking at the reaction of iodine and chlorine coming together to make 2iCl, and they give us a Kp value of 81.9, and they've also given us the initial amounts of our products and our reactants. So if we've got the initial amounts of our products and reactants, and we want to know which direction the reaction will proceed, we're just basically looking for our Q value. So remember, if our Q is equal to K, then we're at equilibrium, so the reaction is not going to move forward or backwards. But if Q is less than K, so Q is smaller, we need it to increase so that it equals K, then we're going to have to make more products, so the reaction is going to have to go forward. And if Q is larger than K, so we need that numerator to get smaller, so we need to take those products and convert it into reactants. So we're going to go in the reverse direction. So if our reaction is shown here, our Q is simply our products over reactants. So we substitute in those concentrations and we find that the Q value is 10.18, which is less than the K, the equilibrium constant. So since K is larger than the Q, so the Q is smaller than the K, the Q's got to increase to be like the K, so the reaction's got to proceed to the right. So this is another reaction that, another example problem that we did in class, and we're looking at PCl5, and we put it into a container and they give us the volume of the container, and they tell us that at equilibrium we've got 0.203 moles of the PCl3 and Cl2 are formed, and they want us to determine the equilibrium concentration of PCl5, and the Kc value is 0.0635. So here we've got the balanced chemical equation, so we need to write what our balanced chemical equation is. So the PCl5 converting into the PCl3 and the Cl2, this is balanced. And our concentrations of our PCl3, so notice that this is a Kc value, so this has got to be in units of molarity. They tell us that we have 0.203 moles of the PCl3, and they give us the volume of the container, so the moles divided by the volume gives us the molarity, so that's where we're going to get the molarity of the PCl3, and we also have the same amount of the Cl2, so now we just need to find the value of the PCl5. So if our equilibrium constant is products over reactants, we're simply going to solve for the PCl5 because this is what we're looking for. And as we solve for the PCl5, we plug in the concentrations. So the PCl3 is 0.406 because it's just these two numbers divided, and then 0.406, and the Kc value, which was given in the problem, that 0.0635, gets substituted in here. And when we do the algebra, the PCl5 concentration is 2.6 molar. So when we're finding the equilibrium concentrations given the equilibrium constant and initial concentrations or pressure, the first thing we need to do is find that balanced chemical equation and set up the ice table. Once we do that, we need to decide which direction the reaction will proceed by comparing the Q to the K. Now I sometimes skip this step because you'll see in a problem later on that the algebra will correct itself, but some people still prefer to do the Q and K comparison. And then we've got to define the changes of all those materials in terms of X, so we basically use X to show how things are changing. And then we're going to have to solve for X in using either the quadratic formula, or we may be able to simplify and approximate answers for very large or small equilibrium constants. But the only time we can do those approximations is when the K value is very large or very small, and even then we have to check to see that the approximation is valid. So here in example 14.11, we're looking at the reaction of iodine plus chlorine to make 2 ICLs at 25 degrees C, and they give us the equilibrium constant using the pressure values. And they tell you that the initial pressure, partial pressures of everything is 0.1 atmosphere, and they want us to find the equilibrium concentrations. So we've got our balanced chemical equation. Now we've got to set up our ice table. So they told us the initial concentrations of everything. So we're actually using the Kp, so we're going to have these in terms of atmospheres. So everything's 0.1 atmosphere. So the change is we're going to represent by X. Here we're going to compare the Q first. So Q products over the reactants, and Q is equal to 1. And since Q is very small compared to the K, so the reaction's got to proceed in the forward direction. So since we're going to assume that the reaction is going in the forward direction, we're going to convert reactants into products. And so as we convert reactants into products, let's subtract for every 1 mole of I2 that combines with 1 mole of Cl2, that'll produce 2 moles of ICl. So these coefficients in front of the changing X, these come from the coefficients in the balanced chemical equation. And these two X's are negatives because we're going in the forward direction, so we're taking away reactants to make products, and as we make products, this is going to be a positive value, so this is going to cause our product concentration to increase. So this would be our equilibrium values. So using our K, so the products over our reactants, we substitute in these equilibrium values into our equation. So the 81.9 is given to us. The 0.1 plus 2x comes from the equilibrium concentration of our ICl over that for our I2 and our Cl2. And using our algebra, these two times each other is squared. So this is just the same information on another slide, just so we have more room to write. Now since we have the squared numerator and squared denominator, we can take the square root of both sides to get rid of that. And then we get the square root of 81.9 equals this. Then it's just algebra to solve for x. So we're just multiplying both sides by the denominator here to get this line here. And then once that we have this line, we are multiplying through by the square root of 81.9. And then we're just rearranging to get all of our x values on the right and our numbers without the x multiplied in front on the left hand side. So we're just doing the algebra so that we can keep solving for x. And then once we add the square root of 81.9x to the 2x, we get 11.05x equals the 0.805, and as we divide both sides by 1105, we get x equals 0.0729. So now that we've got the value for x, now we can substitute into our ICE table and solve for the equilibrium concentrations of each of our reactants and products. So there is our x value that we found on the previous slide. Now we're just substituting in. So the iodide concentration will be the 0.1 minus x, so that'll be 0.0727. The chlorine will also be 0.027, and the pressure of the ICl will be the 0.1, remember, plus the 2x. So as we substitute in the x here, that'll be 0.246. Now if we substitute back in, we can compare just to kind of double check ourselves. And we get a Kp value of 83, and the Kp equals the given within the significant figure. So I know that it looks very different, the 81.9 and the 83. But remember, if we're comparing sig figs, plus or minus 1, so this, if we're reporting this to 2 sig figs, this would be 82, and that would be within the correct sig figs. So we can feel confident that we've done this problem right. Okay, now we're looking at another reaction where we've got iodide breaking up into 2 moles of iodine atoms. So they give us the Kc value, and they give us the temperature, and they give us the moles, and they give us the volume, and they want to know the equilibrium concentrations of our products and our reactants. And we're going to use the quadratic formula to solve for x. So again, remember, we have to have our balanced chemical equation, which they've given to us. Then we set up our ICE table. So our products, and our reactants, and initially we have 0.5 molar I2, because that's the 1 mole of I2 in a 2-liter flask. So moles divided by volume gives us the molarity. And since we don't have any I yet, we know that the reaction is going to go in the forward direction. So since the reaction is going to go in the forward direction, we can subtract out x. So we minus x from the balanced chemical equation. So for every 1 mole of x that we consume, we'll produce 2 moles of 2I. So that's why it's plus 2x here. And so these are going to be our equilibrium concentrations. So if our Kc is products over reactants, our products squared, because that's from our balanced chemical equation over our reactants, and we substitute in. So the Kc value was given to us, the 2x squared, so it's 2x is our product over our I2, and so we get this line here as we multiply both sides by the 0.5 minus x. So this is from just the previous slide. And what we're going to do is we're going to solve and put all the numbers on the right hand side so that we can put in the form that we can use the quadratic equation. So 0 equals everything on to the right hand side. So if you remember your quadratic equation, it's going to be x equals negative b plus or minus b squared minus 4ac. So you take the square root of that over 2a. And remember, only one root will be reasonable, so we'll only keep the reasonable one. And as we use the quadratic equation, remember the coefficient from the x squared, this 4 would be our a, the 3.76 times 10 to the minus fifth will be our b, and the negative 1.88 times 10 to the minus fifth will be our c. So we're just simply substituting in there and solving for x. And so our x value turns out to be 0.00216. So now that we've determined our x value, we can determine our equilibrium concentrations of our products and our reactants. So the 0.5 minus the x equals 0.498, so we can substitute that in there. And then for our I concentration, we said that was going to be plus 2x, so the 2 times the x value. So the I value is going to be 0.00432 molar. And if we want to double check ourselves, we can substitute in those concentrations. Remember, our products over our reactants, and our products are going to be squared because of that balanced chemical equation. So we get a Kc value of 3.75 times 10 to the minus fifth, and that's within sig figs of our given Kc value. So everything looks good. So that's an example where we're using the quadratic formula. Now sometimes using the quadratic formula can be tedious, and sometimes the math can be a little bit tedious. So sometimes we can use approximations. And sometimes approximations can cause us a lot of problems, and sometimes it can be very helpful. So if you're worried about it causing you problems, I would just suggest using the quadratic formula all the time. And this is actually what's suggested by some of the analytical professors. So when you take the quant classes later on, quantitative analysis. Okay, but when you do want to use the approximation, when the equilibrium constant is very small, the position favors the reactants. And when that happens, so when the equilibrium is very small and it favors reactants, it's not going to produce very much products. So that change in x is going to be very small. And so if x is a teeny tiny number, it's going to make a very little difference in the initial concentration. So what we can assume then is that the equilibrium concentration is approximately the same as the initial concentration. And assuming the reaction is proceeding in the forward direction. Now we also have to check the approximation afterwards by comparing it to the approximate value of x in the initial concentration. And if that x value is less than 5% of the initial concentration, then it's okay to use that approximation. So that we take the approximate x over the initial concentration times 100, and if that's at less than 5%, then we can use that approximation value. So here we're looking at hydrogen sulfide being decomposed into hydrogen and sulfur, and they give us a K value, and they also tell us that the volume of the flask is 0.5 liters, and they tell us initially we have this many moles of hydrogen sulfide, and they want us to find the equilibrium concentrations. So they're nice to where they gave us the equilibrium concentration, the balanced chemical equation. Now we just got to start setting up our ice table. So initially we just only have hydrogen sulfide in there, and they tell us the number of moles, and they tell us the volume of the flask. We divide the moles by the volume to get the initial concentration of the hydrogen sulfide, but we don't have any hydrogen or sulfur yet, so we know that the reaction is going to be proceeding in the forward direction. So for every 2 moles of hydrogen sulfide, we're going to produce 2 moles of hydrogen gas and 2 moles of sulfur. So that's where the coefficients come from. So hydrogen sulfide is a reactant. We're going to consume the reactant, so that's why it's a negative. We have the coefficient of 2 in front, so that's why we've got the minus 2x. We're going to produce 2 moles of hydrogen, so that's plus 2x, and then plus 1 mole of sulfur, so that's plus x. So at equilibrium, we just add those columns up, or actually add those 2 rows up. And our K values are products of our reactants. And since we have a 2 in front of our hydrogen sulfide, the hydrogen concentration's got to be squared. And then the 2 in front of the hydrogen sulfide means that the hydrogen sulfide concentration also has to be squared. So we're just taking from our ice table, our products over our reactants, and that equals our Kc value. We can start substituting in. Now because Kc is very small, we're going to approximate that the initial concentration of hydrogen sulfide is equal to the equilibrium concentration of hydrogen sulfide. So to do that, since we're seeing that x is so small, it's not going to change this very much, so we're just going to assume that that initial and equilibrium are the same. But you still don't change the x for the numerator. So since we're assuming that's the same, we're going to get rid of that. So the problem reduces to like this. So then it's a matter of just substituting in our Kc values and multiplying this out, and then solving for x. So we solve for the 4x to the 3rd power, and then we take the cube root, and then we get x equals the 1.38 times 10 to the 5th. So now we have to check to see if our approximation is valid. So to do this, we take our x value over the initial concentration times 100, and it's 5.52%, and that's greater than the 5%, so that approximation isn't valid. So what we can do is we can continue to make approximations. So we're going to use that previous x value from before. Oops. And we're going to substitute that into the K value again. So going back to our initial reaction, so our initial equilibrium constant where we've got the minus 2x, now we're going to substitute in our x that we calculated before when we did the first approximation. So this is where it kind of gets confusing using the approximation, so sometimes I recommend that you just go ahead and use a quadratic first when it gets complicated like this. But if you want to keep using the approximation, you substitute in, and then you solve for x again, and you get a new x value. Now that you got the new x value, you substitute and do the approximation again, and you keep doing it until that your current x value and your new x value are the same. So you're doing a successive approximation. And with this method, if you understand what's going on, you can use it, but for most students I would recommend not doing it because it usually causes more problems than it helps. So using the quadratic would probably been easier for most students. So now that we've done the successive approximation so that we finally get x coming out to be the same number each time, now we can substitute in to find our equilibrium concentrations of the hydrogen sulfide and the hydrogen and the sulfur. So we just simply substitute the x in to find the concentrations. Now we can plug those values back in to compare our K values. So if we plug those in, we get a Kc value of 1.67 times 10 to the minus 7th, and this agrees with our given K value. So this approximation using the successive method actually worked, and so we can feel confident with our answer. Okay, so here we're looking at the I2 getting converted to 2 I's. So this is the same problem that we looked at before where we use the quadratic equation. Here we're simply just using the approximation method. So we're just comparing the two. So this is the same problem as the problem before last. So again, we've still got our initial values, the 0.5 and the 0, and the change is minus x and plus 2x, and our equilibrium values. And so we're going to proceed in the forward direction because we don't have any of our product produced yet, so we're going to definitely have to go in the forward direction. And we've got our K is our products over reactants, so our products has a coefficient of 2, so it's going to be squared. And our Kc value is 3.76. We just simply plug this in here. And so here we're plugging in here. So this would be our normal Kc value after everything's plugged in. But because the Kc value is a very small value, we're going to assume that maybe x is such a small number, it's going to be insignificant when we subtract out this very tiny number from the 0.5. So this is where we're making the approximation. So as we go from this part of the equation to here, we just said x is really small compared to this number, so it's not going to make a difference. We just simply drop it out. And then so once we made that assumption, we multiply both sides by the 0.5 and equals a 4x squared. So here's where we were on the previous slide, and we just simply solve for x, and x equals 2.17 times 10 to the minus third. So notice that we didn't have to go through the problem of using the quadratic equation, but since we did do the approximation, now we have to test to see if it's valid. So the x over the initial concentration times 100, and that changes 0.434%, so it's definitely less than the 5. So it's okay to use the approximation in this case. So now that we have our x value, now we simply just substitute in for our equilibriums, just like we did once we used the quadratic. And we find our I2 and our I concentrations, and we check everything. So we take the I2 over the I squared over the I2, and we get a Kc value of 3.78 times 10 to the minus 5th. And within the sig figs, we're okay. So we get the same Kc value, so everything looks good. Okay, so here's our last problem to look at. And in this one, we're looking at hydrogen bromide getting converted into hydrogen and bromine. And they tell us the concentrations, the initial concentrations of everything that we've got into this container, and they want to know the equilibrium concentration of HBr. Now, some people recommend, to do the K versus Q comparison, but here's where I'm going to show you why I don't do that comparison at first, and why the algebra will actually save you the step and the time. So our first step, we look at our equation, make sure it's balanced, and then we've got our balanced chemical equation. And then we set up our ice table. So initially we have 0.2 atmospheres of HBr, 0.01 atmospheres of the H2, 0.01 of the Br2. And our change is going to be for every 2 moles of HBr. So if we're going, I like to just assume we're going the forward direction. So we're going to subtract 2x from there. That's going to make x 1x of H2 and 1x of Br. So our equilibrium concentration is going to be the 0.2 minus the 2x for the HBr. The H2 is going to be 0.01 plus x, and the Br is going to be 0.01 plus the x. Okay, so now I'm using my K value. So remember, our K is simply our products over reactants. And so we're using pressure here in atmosphere. So the pressure of H2 times the pressure of Br2 over the pressure of the HBr. And remember, that's got to be squared because of this coefficient of 2 up here. And because the pressure of the H2 and the pressure of the Br2 are the same, we can simply just square that, the 0.01 plus x squared. And they gave us the KEQ, the 4.18 times 10 to the minus 9. So that's where this value comes from. So now I need to just start solving for x. So what's going to make my life easier is if I just take the square root of both sides. So there's where I start taking the square root. And then as I start doing the algebra, I get an x value of minus 0.00999. So this is telling me that I'm not too worried about having a negative x value. So what this tells me is that rather than proceeding the forward direction, I'm actually need to go in the reverse direction. So this is why I didn't bother comparing K versus Q, because this negative sign in my x will tell me what I need to do. So once I get my x of negative 0.0099, I simply substitute that because we're looking for the equilibrium concentration HBr. So that's just the 0.2 minus the 2x, so 0.2. So where's my little pointer? So the 0.2 minus x, so the x, remember, was this negative value here times 2, and the HBr concentration, or the pressure is going to be 0.22 atmosphere, and that's not one of our options, so we would select E. None of the above are correct. Okay guys, so that's some good example problems, and hopefully this is very useful and helpful to you. And if you've got questions, please let me know.